Have a look at another example. In this case, we're going to look at this series, the harmonic series, sum of 1 over n. And we're going to make the connection between this series and the integral of from 1 to infinity of 1 over x dx. We may recall from a previous lecture that the harmonic series diverges. We're not going to use that here. What we're going to do is come up with a completely independent argument of that previous one that again shows that this series diverges. And we're going to do that by connecting it with the integral. So again, let's draw some stuff in our diagram. I'm going to use some rectangles again. And here, I'm going to draw the rectangles in this way. Draw them slightly overshooting the area under the curve. In other words, I'm using the left-hand endpoints of each subinterval to construct the corresponding heights of these rectangles. And what I'd like to do is make a connection then with the area of these rectangles and our series, and a connection with the area of the rectangles and the area under the curves. Let's look at, first of all, the area of the rectangles. How does the area of the rectangles compare? I should put an E there. How do the area of the rectangles compare with the area under the curve? Well, the areas under the rectangles are covering all the area under the curve plus some more stuff above, so we know that they have to be bigger than the integral from 1 to infinity of 1 over x dx. Okay, and what are the area of the rectangles? Well, the heights here, this was y equals 1, the height here was y equals 2, the height here was y equals, 1 half, y equals 1/3, y equals 1/4. And so our areas of our rectangles are given by 1, 1/2, 1/3, 1/4, and so on. So this is 1 plus a half plus a third plus a quarter plus dot dot dot. And this is supposed to be bigger than the area under the curve, or the integral from 1 to infinity of 1 over x dx. And this sum is precisely our series that we're interested in finding some information about. And we have indeed found some information. We found that our series, the sum of our series, is bigger than this integral. And so the question is, what's the integral then? Well, this is something we can work out. The integral, antiderivative of 1 over x is ln of x. We're evaluating from 1 to infinity, so we should really use a limit here. Limit as m goes to infinity of ln of x from 1 to m. And so as m goes to infinity, ln of m goes to infinity, so this diverges. So our integral diverges to infinity, and our sum has to be bigger than it. So it must also diverge to infinity. So that diverges too. And so there we go. What we've done is we've taken our series, which we had some questions about, convergence, divergence. We've made the connection with the integral of the corresponding function 1 over x. Our integral represents the area under the curve, which we found to be infinite. And so our rectangles, which cover that area, but then also a little bit more, must also be infinite. And so our series, which represents the area of those rectangles, must diverge too. So in both these examples, we saw that we can get information about the series by looking at the corresponding integral. If the integral converges, it might be enough tell us that the series converges. If the integral diverges, then that might be enough to get that the series diverges. The key fact, though, was really getting these inequalities in the right direction. Right? In this case, we had that our series was bigger than something, and that something was going to infinity. So our series was getting bigger than something that is already infinite. So it has to be infinite as well. Whereas our previous one, we had that our series was smaller than something finite. So it had to be finite as well.